So today's topic is division properties of exponents. And I've got a couple division facts below. We know 32 divided by 4 can also be written vertically as 32 divided by 4. Either way, they both equal 8. We also know that 32 is the same as 2 to the 5th, and 2 is the same as 2 squared. If I look at the answer 8, that's 2 cubed. And we look at the relationship between 2 to the 5th over 2 squared equaling 2 cubed, and we can clearly see that if we subtract the exponents while keeping the base the same, we get the solution. So in general, here's a rule: given two exponent terms with the same base, we keep the base the same and subtract the exponents. That base raised to the a over that base raised to the b is equal to that base to the a minus b power. Here's a couple other properties we need to know about. If we have a fraction raised to a power, then that's the same as the numerator raised to that power over the denominator raised to that power. An example would be 3/5 raised to the third is equal to 3 to the third over 5 to the third, or 27 over 125. Now here's another topic or equation we know to be true. Anything over itself is equal to 1, so 25 over 25 is equal to 1. Apply this new concept in terms of powers. 5 to the second, which is 25 over 5 to the second. We keep the base the same, subtract the powers, so that's 5 to the 2 minus 2 is equal to 5 to the 0. Well, 5 to the 0 then must equal 1. And likewise, we can state another rule that any base raised to the 0 power is equal to 1. So here is that. Any base n raised to the 0 power is equivalent to 1. It's always going to be true. When we talk about negative exponents, notice here we have 8 over 32, which is 2 to the third over 2 to the fifth, which is 2 to the 3 minus 5, or 2 to the negative 2. We know that 8 over 32 is the same as 1/4. So 1/4 must be equivalent to 2 to the negative 2. We know that 4 is equivalent to 2 squared. So 2 to the negative 2 must equal 1 over 2 squared. And in general, we can write a little rule for this. For any non-zero number, so that base number is non-zero, and having exponents n, then any base raised to the negative power is the same as the reciprocal of that base to the power. So I have a couple examples for us. 3 to the negative 2 is equal to the reciprocal of 3 to the positive 2. So 3 to the negative 2 is 1/9. Likewise, if I have a reciprocal already, or 1 over a base raised to a negative power, then I take the reciprocal of that. If it's in the denominator, it goes to the numerator and is now raised to the positive power. Again, here's m to the negative 5th. That's the reciprocal of m to the 5th. When I have a fraction raised to a negative power, I can either do one of two things. I can take the reciprocal of that fraction and raise it to that power, or I can say I have a term raised to a power, so that's 2 to the negative 2 or 5 to the negative 2. Each base has a negative exponent, so take the numerator, put it in the denominator, that's the reciprocal, put it to the positive power. Denominator goes to the numerator, that's the reciprocal, and give it to the positive power, and then square both, so I get 25 over 4. It's going to be an important concept. So now we're going to go through a series of exercises, and I will take and show you a couple of different ways I would go about solving these. In our first example, we notice we have 16 over 6, neither of which is a base of any exponent. So this is just a number. In fact, I'm going to separate it for us so we see that. 16 over 6, and then I have a to the 5th, b to the 20th, over a to the 12th, b to the 3rd. I handle my numbers different than I do my exponents. So 16 over 6, I know that 2 goes into both, 8 and 3 times. And then for my exponents, I have 5 and 12 as the same base of a, so I take 5 minus 12. And I have a base of b and take 20 minus 3. Now, in this case, we subtract these and have 8 over 3, and this is a to the negative 7, and b to the 17th. Now, typically they ask to give answers with no negative exponents. So if I see this negative exponent, I take its reciprocal, and since it's in the numerator, I'll put it in the denominator, and I have the positive power now. And this is my final solution. In this problem here, I see I have a power raised to a power, so I'm going to take and multiply those powers. That's x to the 10th and y to the 25th over y to the 40th and z to the 15th. I look for the same base. X doesn't have the same base anywhere, so that's x to the 10th. Y has the same base, so that's y to the 25 minus 40. And z is in the denominator. So I'm going to keep it in the denominator and make that to the 15th. I subtract these two. I notice I have x to the 10th, y to the negative 20th, and z to the 15th. Instead of having a negative exponent, I bring it from the numerator to the denominator, making its exponent positive, and z is still in the denominator. Now, I want you to notice a couple of things here. If I were to take and look for the greatest exponent of each base, so for a, the greatest exponent was 12, and if I take 12, subtract from 5, I get 7, and there it is. And then if I were to find my greatest exponent of like bases here, I have 40 and 25. Subtract 40 minus 25, I get 20. Notice where it appears. In this problem over here, I have 20 and 3. Take 20 minus 3, get 17. Notice where it appears. In each case, you'll notice the answer of the greatest exponent appears wherever the greatest exponent is after subtracting, if that makes any sense to you. So I've got a little bit of rule here. Find the greatest exponent of the base, and the solution will be on that half of the fraction. So I'll go through and do a couple more examples using this concept. Let's go here. I have 12 to the 14th. This is a power raised to a power, so I'm going to multiply powers. Remember, you have that unwritten power of 1 on the 3, so I have 12 x to the 14th over 3 squared x to the 20th. Let's just simplify that a little bit. That's 12 x to the 14th over 9 x to the 20th. So in this case, I look at my numbers, 12 and 9. 3 go into both. 4 on the top, 3 on the bottom. And now we're going to use that principle of finding the biggest exponent power, which is 20, keeping my answer on that half of the fraction, and then subtracting the powers. 20 minus 14 is 6. That way I avoid going, well, I have a negative exponent and then I have to bring it down to the denominator. So this is 4 over 3x to the 6th. Likewise, in this problem, what I prefer to do first, and some people may differ in this opinion, but I like to take and make sure all my exponents are positive to start with. So I have x to the 7th, I have x to the 4th in the denominator. This y is to a negative power, so I'm going to move it from the numerator to the denominator, make its power positive, and y to the 14th was initially positive, so I keep it where it is. So now what I'm going to do is my multiplications first. I see I have a multiplication of y to the 12th and y to the 14th, which means I keep the base the same and add the powers. So I have x to the 7th, x to the 4th, y to the 26th. And then I'm going to take and find the greatest exponent for the same base, since I have a fraction. And I'm going to keep my x solution in the numerator, because that's where the biggest exponent is. Subtract 7 minus 4, which gives me 3, so I have x to the third, and y stays in the denominator. Let's do the next one. Again, I have a couple options here. I prefer to do all my powers of powers first, if you will. So in this case, there's that unwritten power of 1 here. So what I have is I have 24 to the negative 1 since I'm multiplying powers, x to the negative 5, y to the positive 7, over 2, x to the negative 8, and y to the 13. Once again, I like making all my negative exponents positive, which means taking reciprocals. So 24 moves from the numerator to the denominator, and it's to the first power, so that's just 24. X to the fifth moves to the denominator. Y to the seventh stays where it is. 2 stays where it is. X, since it's to the negative 8, moves to the numerator, and it becomes a positive 8. And y stays where it is. So now I take a look and see if I have any multiplications I can do. Certainly I do. I have this 2 and the 24, which makes a 48, and that's in the denominator. And now I'm going to find the greatest powers of like bases. So 7 is the greatest power, or I lied. It's actually not. 13 is the greatest power of the base y, and 8 is the greatest power of the base x, and then I'll take and subtract and place my answers where the greatest exponent is. So if I use my x, 8 minus 5 is 3. Greatest power is in the numerator, that's where the answer is. 13 minus 7 is 6. Since my greatest power is in the denominator, the answer for the y's is in the denominator. And there I am. So in this last example, you'll notice we have a fraction raised to a negative power. Now, you can do this a lot of different ways, and just for argument's sake, I'll do what's inside the parentheses first, and then I'll bring my negative 2 in. It's a little bit different than I did the last problem, and the only reason I say that is, in this case here, I have a 6 and a 14. And rather than making this problem a lot bigger by squaring this and squaring this, I can reduce these two first. In fact, maybe that's all I'll do first. So I know a 2 goes into 6 and a 2 goes into 14. 2 goes into 6 3 times. And 2 goes into 14 7 times. So that's the only reduction I'm going to do first. And then I'll say that's x to the 9th, y to the negative 10th. That's x to the 4th, y to the 6th. And that's still to the negative 2. So now I'll go ahead and raise the power to the power. Again, remembering that I have powers of 1 on both the 7 and the 3. So this is 3 to the negative 2, x to the negative 18th, y to the 20th, over 7 to the negative 2, x to the negative 8, and y to the negative 12. I'm going to make all my negative exponents positive exponents by taking reciprocals. The 3, since it's a negative exponent, moves down. Exponent becomes positive. X, negative exponent, moves down, becomes positive. Y to the 20th stays where it is. Let's go down to the denominator. 7, since it's a negative exponent, is going to take and move to the numerator. Exponent's positive. X to the 8, negative. Exponent moves to the numerator. Exponent becomes positive. Y, negative 12th, moves to the numerator, becomes positive exponent. I'll multiply anything together that I can. I see a 7 squared, which is 49. I see an x to the 8th. And y to the 20th and y to the 12th. Keep the base the same. Add the powers. Over 3 squared, which is 9. And x to the 18th. 49 over 9 goes nowhere. X has a common base with the x in the denominator. Find the greatest power and subtract, keeping the x answer in the denominator. So I have the 49 over 9 left. X to the 18 minus 8 is 10. And then I have y to the 32nd.